Hello. Good evening, all. I am Saurabh and I welcome you to this session for the NPTEL course Applied Thermodynamics. So, this was a 12-week course and we have already completed our 12 sessions. So, this is an extra session. So, it will be like revision of all the topics that we have covered. So, basically, in this session, we will try to solve some problems. Most of them will be numerical problems, at least one from each chapter. Okay. So, let us start. So these are the modules which we have covered. We discussed basics of thermodynamics. We discussed steam power plant, then internal combustion engines, then gas turbines, then refrigeration and air conditioning systems, and reciprocating air compressors. Okay. So we will begin our discussion with question number 1. Question number 1 says there is one relation TdS is equal to du plus PdV is valid for. Okay, so this is very useful relation. You might have encountered with this equation many times. So we have to tell in which situation this is valid. So basically this equation is just another form of first law of thermodynamics. So if you write like this, dq is equal to dE plus dW, then for reversible processes, you can write dq is equal to TdS, and for simple compressible systems, you can write dW is equal to PdV. Okay. So for this relation, dW is equal to PdV, there are two assumptions that system should be simple compressible system, but the system should also be reversible, right? So if you substitute these values, these relations for Q and W, then you will get TdS is equal to du plus PdV. Okay, and of course and we are assuming that there is no changes in potential energy, kinetic energy, and other forms of energy. There is only changes in internal energy. Okay, du. So from for reaching from this original equation to this equation, there are few assumptions that it should be reversible. There should be no other type of interactions. Only change in potential and only change in internal energy. Okay, and system should be simple compressible system. Then we reach. Then we get this equation. Okay. So you may think that for this final equation to be valid, this final equation can be valid only if the system is reversible and system is simple compressible, and all these assumptions should be there. Then only this equation will be valid, but it is not like that. Why? Because all the quantities involved in this equation are point functions. Okay, they are properties. For example, temperature, entropy, internal energy, volume, pressure, they all are point functions. Okay, properties. So they are not path functions. Okay, so they does not depend on the nature of the process. Okay, it does not depend on which path the process is taking place. So they are point functions, so it is always valid. Okay, so it is always valid. If the equation involves some path function, then it depends on the nature of path. But here there is no path function. All the quantities involved are point functions, so it is always valid. Okay, so this is a very important point to note. that this equation is always valid. So this thing make this equation very powerful, because you can always use this equation, right? And whenever you want to use equation when there are path functions, then you have to be little more careful. Okay, but here, this equation is always valid. So the option, which option should be correct? First option is reversible processes, irreversible processes, isentropic processes, and it is saying never valid. Okay, so of course it is always valid. So okay, so this may be the correct option. Okay, a reversible process as well as irreversible as well as isentropic. Okay, so I hope that this is clear, and we can move to the next question. Question number 2. It says that at 100% relative humidity, the wet bulb temperature is option A, lower than the dew point temperature, higher than the dew point temperature, C, equal to the dew point temperature, or none of the above. So this is from the psychrometry, and I hope that you can easily answer this question. At 100% relative humidity, you know that wet bulb temperature, dry bulb temperature, and dew point temperature, they all are equal, right? You know what is dew point temperature? Dew point temperature is uh, temperature. You can think in this way, like you have a mixture of air and water vapor, and you cool that mixture at constant pressure. So at some point you will reach 100% relative humidity. Okay, so condensation will start. So that temperature, when this condensation start or you reach the 100% relative humidity, that is called dew point temperature. Okay, so at 100% relative, at 100% relative humidity, the wet bulb temperature and dew point temperature are same. Why? Because dew point temperature is defined in this way, and since the relative humidity is 100%, so the dry bulb temperature and wet bulb temperature will be equal, because no more uh, evaporation can take place. So there will be no cooling to reduce the wet bulb temperature. Okay, so basically what I mean is, at 100% relative humidity, wet bulb temperature, dry bulb temperature, and dew point temperature, they all are equal. Okay, so option C should be the correct option in this case. Okay, other options are not correct. Okay, okay, so I hope there is no difficulty and we can move ahead. Okay, so we will move to the question number 3. Here is question number 3. Let us read this question. This is numerical question. It says that an aircraft engine operates on a simple ideal Breton cycle. So you have studied the Breton cycle with a pressure ratio of 10. Okay. The heat is added to the cycle at a rate of 500 kilowatt. This is the rate of heat addition. The air passes through the engine at a rate of 1 kilogram per second. Okay. And the air at the beginning of the compression is 70 kilopascal and 0 degree Celsius. We have to find the power produced by this engine and its thermal efficiency. And we can use the constant specific heats at the room temperature. Okay, so this is simple question based on Breton cycle. Okay, we can easily solve this question. First, we should make the TS diagram. Okay, from 1 to 2, you have compression. In ideal case, it will be isentropic compression. Then you have constant pressure heat addition. Then 3 to 4, we have turbine. In ideal case, this will be an isentropic process, isentropic turbine. Then you have heat rejection or exhaust. Okay. So I will write down the processes. 1 to 2, this is isentropic compression in compressor. Then 2 to 3, this is constant pressure heat addition. Then 3 to 4, this is isentropic expansion in the turbine. And 4 to 1, this is constant pressure heat rejection. Okay. It is given that we can use the constant specific heats at the room temperature. So at the room temperature, you can check the tables for properties of air. So you can find the values of specific heats. Okay. So at room temperature, I will write the value of specific heat of air at room temperature. At room temperature, Cp is 1.005 kilojoule per kg Kelvin, and K is 1.4. Okay, K or gamma, whatever you want to write. So it is up to you. Okay. We have been given some value in the question itself, right? For example, at point 1 at the beginning of compression, the pressure and temperature is given, right? What is given? T1 is given, right? This very. T1 is given 70 degree, right? Sorry, 0 degree. So it is 273 Kelvin. Pressure is given, P1 is equal to 70 kilopascal. Okay. To find these values at point 2, we'll have to use adiabatic relation. Okay. So what is that? P1 V1 to the power K is equal to P2 V to the power K. Okay. In terms of temperature, you can write this thing as P1 instead of V, you can write T by P, T1 by P1 to the power K is equal to P2 T to the T2 by P2 to the power K. Okay. And from here, you can write T2 is equal to T1 into P2 by P1 to the power K minus 1 by K. Okay. Or you can write it as T2 is equal to T1 into RP. Okay, so RP is nothing but the pressure ratio. Okay. RP to the power K minus 1 by K. Okay. So T1 we have, RP also we have. Okay. What is RP? RP is given here 10, right? So RP is 10. T1 is also given. It is 273 Kelvin into 10 to the power k minus 1. So it is 0.4 divided by k, it is 1.4. So if you calculate this value, then you will find the T2. Okay. So 273 into 10 to the power 0.4 divided by 1.4. Okay. It is 527, 527.08 Kelvin. Okay. So now you have temperature at 0.2, right? So we have temperature at 0.1. We have calculated the temperature value at 0.2. Now we need this value at 0.3, right? So from 0.2 to 0.3, there is constant pressure heat addition, correct? So temperature at 0.3 should be equal to T2 plus Q in, whatever heat input per unit mass of air, divided by Cp, correct? Because T3, because heat input will be given by Cp, T3 minus T2, correct? So this Q in is heat addition per kilogram of air. So here it is given that 5 kilowatt of heat is being added and air flow rate is 1 kilogram per second. Okay. So Q in will be equal to 500 kilowatt for 1 kg of air. Okay. So it is 5 kilowatt per kg. Okay. So T3 you can write it as T2 we have already calculated as 527.08 plus 500 divided by Cp. What is Cp? Cp, we are using this value of Cp. This you can check in any property table for air. Okay, Cp we are using 1.005. 1.005. Correct. So if you calculate this value, then we will get C3. Okay, 527.08 plus 500 divided by 1.005. So it is coming out to be 1 point, sorry, okay, 1024.59. We are getting T3 is equal to 1024.59 Kelvin. So this is T3. Okay. So now we have temperature value at 0.3. Now coming to 0.4. So 3 to 4 is again an isentropic process. So you can use adiabatic relation. Okay. So again you can write T4 is equal to T3 into 1 by Rp to the power k minus 1 by k. Okay. So this is coming from P4 V4k is equal to P3 V3 to the power k. Okay. If you just substitute the values, T3 we have just calculated, pressure ratio is 10 and k is how much? 1.4. 0.4 divided by 1.4 Kelvin. One 0.24.59 into 1 by 10 to the power 0.4 divided by 1.4, and you have 139.68. Sorry, 130.68. So we have T4 is equal to 530.68 Kelvin. So now we have temperature values at all the desired points. Okay. Now we can calculate whatever is asked. What is asked? We have to find the power produced by this engine. Okay. Power produced. So what will be the net power produced? So power will be produced by turbine, but some power will be consumed by compressor. Okay. So net power produced will be power output of turbine minus power input to the compressor. Correct. So we need these two values, power output of turbine. So power output of turbine will be equal to Cp, where is turbine? 3 to 4. Okay. So Cp T3 minus T4. Cp is 1.005. T3, how much is T3? T3 is 1024.59 minus T4 is 530.68 Kelvin. Okay. So we'll get this value in kilojoule per kg. 1.005 into 1024.59 minus 530.68. Okay. So it is coming out to be W2 WT, that is work produced by turbine, 496.38 kilojoule per kg. Okay, so this is work output of turbine, but we also need work input to the compressor. Okay, work input to the compressor. So this will be equal to Cp, and where is the compressor? Compressor is from 1 to 2. Okay, so T2 minus T1. Okay, 1.005. T2, how much is T2? 527.08. So 527.08 minus T1. How much is T1? T1 is 273. 273. So again, we will get this value in kilojoule per kg. 1.005 into 527.08 minus 273. So compressor work is 255.35 kilojoule per kg. So the net work output, how much will be the net work output? Turbine work minus compressor work. So 496.38 minus 255.35. So it is coming out to be 241.03. So this is the net work output. Okay. So this is the answer. What else we need to find? Power produced by this engine. Okay. So this is power produced. So 1 kilogram of air is passed in 1 second. So this is in, you know, kilogram per kg of air, but 1 kg of air is passed in 1 second. So this you can write it as 241.03 kilojoule per second. This is nothing but kilowatt. Okay, 241.03 kilowatt. This is the power production. Okay. What else? It's thermal efficiency. We also need to calculate the thermal efficiency. Now coming to thermal efficiency. So thermal efficiency is defined as net work output divided by heat input. Correct? So how much is the net work output? It is 241.03 kilowatt divided by heat input is 500 kilowatt, right? 500 kilowatt. Forty-one 3 divided by 500 kilowatt. So it is coming out to be 0.482. Okay. So thermal efficiency is 48.2%. Okay. This is the thermal efficiency. Okay. I hope it was easy for you to solve this question. Only thing is you need to make the TS diagram first, then you need to find the uh, remaining values of temperature at all the points, and it is just straightforward. Okay. So if it is clear and there is no doubt, then we can move to the next question. Question number 4. It is saying that an air standard diesel cycle has compression ratio of 16 and cutoff ratio of 2. Okay. At the beginning of compression process, air is at 95 kilopascal and 27 degrees Celsius. Accounting for the variation of specific heats with the temperature, we have to find the temperature after the heat addition process, thermal efficiency, and the mean effective pressure. Okay. So again, we will start by making the diagram first. Okay. So in this case, we will make a PV diagram. Okay. First of all, there is compression 1, 2, 2. This is isentropic compression. Then there is constant pressure heat addition 2 to 3. Then there is power stroke, expansion. then there is constant volume heat rejection. Okay. So what is given? Compression ratio is given. Okay. So P2 by P1 is given 16. Cutoff ratio is given 2. And at the beginning of compression process, the pressure is given, P1 is given 95 Kelvin kilopascal, and temperature T1 is given 27 degrees Celsius. So 273 plus 27 Kelvin, or you can write it as 300 Kelvin. Okay. Accounting for the variation of specific heats with the temperature. Okay. So you know that specific heat depends on the temperature. In the previous question, we have assumed that specific heats were constant at with respect to temperature, but here we have to consider the variation of specific heats with the temperature. So we need to use the tables, right? Property tables for air. Okay. So let us open the tables. Okay. We need the property table for air. Properties of atmosphere at higher temperature. Okay. So ideal gas properties of air. So we have T1 is equal to 300 Kelvin. 300 Kelvin. So we need to look these values at 300 Kelvin. So where is 300 Kelvin? Here is 300 Kelvin. So at 300 Kelvin, we have U is equal to 214.07. U is equal to specific internal is equal to 214.07 kilojoule per kg. Okay. And VR is 621.2. VR1 is equal to 621.2. Okay. So VR2 will be V2 by V1 into VR1. Right? And compression ratio is given to be 16. Correct? Okay, sorry. So compression ratio V2 by V1, this is given to be 16. And VR1, we can use this value. Okay. So we can substitute these values and we can find VR2. So it is coming out to be 16 into This is V1 by V2. Okay, so VR2 is equal to 1 by 16 into what is VR1? 621.2. Okay, so get 621.2 divided by 16. So it is 38.825. So this is VR2. Okay. Then process 2 to 3. This is constant pressure heat addition. Okay. So for constant pressure, you can use this relation. V3 divided by T3 is equal to V2 by T2, right? So from this relation, you can find T3, and T3 can be given as written as V2 into T2. Okay. So V3 by V2, it is given cutoff ratio. Where is the cutoff ratio? It is given to be 2. Okay. So it is given to be 2. So 2 into what is T2? T2 we have just found. Where is T2? Okay, probably we have not find out yet T2. Okay, we have found out VR2. From VR2, we need to find out T2. Okay, so let us find that value first. Okay. From here, you can write T2 is equal to 862 point using the VR2. You can write this as 0.4 Kelvin. I'm writing directly. You can check the calculations. And H2 is equal to 890.9 kilojoule per kg with these values. Okay, so T2 you can write here as 862.4 Kelvin. So T3 is coming out to be 1724.8 Kelvin. Okay. Similarly, you can write H3 equal to 190 from the table. So it will be somewhere between this value, right? So H3 will be equal to, taking this value, 7124. 1724. So it should be somewhere around this value. Okay, so H3 will be somewhere around this value. You can use the interpolation. I'm writing the direct value and I am taking 1910.6 kilojoule per kg. Okay, and VR3, this also will be between somewhere between this value. Okay, so again you can use the interpolation. I am writing 4.546. Okay, so okay, so we were asked to find the temperature after heat addition process that we have calculated. Okay, so T3 we have calculated, correct? So this is the temperature after heat addition process. Now come to the next question. The thermal efficiency. Thermal efficiency is given by 1 minus Q out by Q in, right? But to calculate Q out, you, you can write it as Q4 minus Q1, right? And you have U1, but you need to find U4, right? And to find U4, you can use this relation. VR4 is equal to V4 by V3 into VR3 is equal to V4 by 2V2 because V3 is equal to 2V2, right? This is cutoff ratio into VR3, correct? So you can write as R by 2, okay, R by 2 into VR3 is equal to 16 by 2 because R is 16 into VR3. How much is R3? This is R3. 4.546. Okay, so if you calculate this value, then it will come out to be VR4, it will come out to be 36.37. Okay, so from here you can calculate U4. So U4 will be equal to 659.7 kilojoule per kg. So now you have U4 and you have U1, right? So you can calculate Q out. Okay, so Q out will be U4 minus U1. U4 you just got 651.7 and U1 is how much? Here it is 214.07. 214.07. Okay, kilojoule per kg. Okay, so Q out is coming out to be, I'm 659. 445.63 kilojoule per kg. Okay, so Q out is 444.63 kilojoule per kg. What else we need? We need Q in, correct? We need Q in, and Q in is H3 minus H2, right? So H3 we have, where is H3? Here is H3, 1910.6 minus H2, where is H2? H2 is 890.9. Again, kilojoule per kg. This is our Qin. Now you can calculate the thermal efficiency. Minus Q out by Qn. So 1 minus 444.63 divided by how much is Qn? 1910.6 minus 890.9. 1019.7. Have we already have this value? Do we already have this value? Okay. Anyways, so this will be the thermal efficiency. Let us calculate this value. 445.63 divided by 1019.7. So we are getting 56.29. Okay, so it is coming up to be 0.5729798. So thermal efficiency is 56.3%. Okay. What else we need to calculate? The mean effective pressure. So mean effective pressure is net work output divided by change in volume, shaft volume. What will be the net work output? Net work output will be equal to Q in minus Q out. So what is Q in? This is Q in 1019.7. And Q out is 444.63. It's coming out to be 574.07. Now we also need V1. V1 will be equal to, from the ideal gas equation, you can write RT1 by P1. Okay, so R is 0.287 for air. Again, I'm not writing the unit, everything is in SI unit, 95. So please do this calculation by yourself and check if you are getting this value, 0.906 meter cube per kg. Okay. And V2 will be V1 by R, compression ratio, correct? So now you can substitute all these values for calculating the MEP, mean effective pressure. Mean effective pressure is net work output, that is net work output minus V1 by V2. Net work output is 574.07. V1 is 0.906 meter cube per kg, and V2 is V1 by R. And R, that is compression ratio, it is given in the question and it is 16. Okay, so you can just substitute the values. 574.07 divided by 0.906, 1 minus 1 by 16. It will be in the kilopascal. Okay. So we are getting 675.87 kilopascal. So this is the MEP. Okay. So we were supposed to find temperature after the heat addition process, that we have got E3. Okay. And we were asked to find thermal efficiency and mean effective pressure. So thermal efficiency we have calculated, and it is coming out to be 56.3%. And mean effective pressure also we have calculated, and it is 675.87 kilopascal. Okay. So I hope everything is clear in this question. So if there is no doubt, then we can move forward to question number 5. Okay. Question number 5 says, a steam power plant operates on an ideal Rankine cycle with 2 stages of reheat and has a net power output of 75 megawatt. Okay, so there is a steam power plant and it has 2 stages of reheat. Okay, ideal Rankine cycle, 2 stages of reheat. net power output of 75 megawatt. Steam enters all three stages of turbine at 550 degrees Celsius. The maximum pressure in the cycle is 10 megapascal and the minimum pressure is 30 kilopascal. The steam is reheated at 4 megapascal at the first time and at 2 megapascal at the second time. We have to show the cycle on a TS diagram with respect to the saturation lines, and we have to find the thermal efficiency of the cycle and mass flow rate of the steam. Okay. Okay. So first of all, we will make the TS diagram because it is asked. Even if it was not asked, we should make the TS diagram. One to two is pump, then boiler, from 2 to 3. This is constant pressure heat addition. Then again another stage is a first turbine, then one reheat, one more turbine, and one more reheat. Okay, so it was given that there are two stages of reheat. So 2 to 3, this is constant pressure heat addition in the boiler. Then 3 to 4 is the first turbine, 4 to 5 is the first reheat, 5 to 6 is second turbine, 6 to 7 is another reheat, and 7 to 8 is the turbine. So this is whole process on yes diagram. We can also write these pressure values. The minimum pressure is 30 kilopascal. Okay, so minimum pressure is 30 kilopascal. Maximum pressure is 10 kilopascal, right? It is given. Okay, so this is maximum pressure. Then 5 to 4, it is 4 megapascal first reheat, and the second reheat is 2 megapascal. Okay, so this is the TS diagram. So what we have to find? We have to find the thermal efficiency. So we will require the properties of a steam. So we will have to use the steam table. Okay. So let us start from point 1. So point 1 is at the saturation line. So H1 will be equal to enthalpy of saturated liquid at this given pressure. Okay. So we will use the saturated steam table. Here it is. At what pressure? 30 kilopascal. 30 kilopascal. What we need? We need enthalpy of saturated liquid. So enthalpy of saturated liquid is 289.27. So it is 289.27 kilojoule per kg. Okay. And specific volume at this point is this 1.001022 meter cube per kg. Okay. So now we can calculate the pump work. Pump work will be equal to specific volume minus increase in pressure. So this we have just find from the table, and the pressure at P2 is 10 kilopascal, 10 megapascal. Sorry, this is 10 megapascal. 10 megapascal minus 30 kilopascal. Okay. If you calculate this value, it will come out to be, I'm writing the final value. You please do your calculation and check if you are getting the same value or not. So if there is any mistake, just let me know. So this is pump work. Now you can find the enthalpy at point 2. Enthalpy at point. So point 2 is in the subcooled region. Enthalpy at point 2 will be equal to enthalpy at point 1 plus work done by the pump. Correct? So enthalpy at point 1 we have already got from the table. It was 289.27 plus pump work we have just calculated. So now we have enthalpy at point 2, H2 we have. Okay. So H2 is coming out to be 299.37 kilojoule per kg. Okay. So now we have values at point 1, at point 2, right? Now we need values at point 3. Okay. So here is point 3. Point 3 is in the superheated region. Okay. So point 3. So pressure at point 3 was maximum pressure. How much? 10 megapascal, correct? And temperature was 550 degrees Celsius. So now you have to use superheated tables, right? These are the superheated tables. Okay, so 10 megapascal at 550 degrees Celsius. Okay, we have H3 equal to 3502. We have H3 equal to 3502.0 kilojoule per kg. And S entropy, we have 6.7585 kilojoule per kg Kelvin. Okay, so now we have values at 0.3 and we need values at 0.4. At 0.4, pressure is given in the question, and it is given that pressure of first reheat was 4 megapascal. Okay, and entropy at 0.4 will be equal to entropy at 0.3 because process 3 to 4 is an isentropic expansion in the turbine. Okay, we'll use 4 megapascal. There is 4 megapascal, here it is 4 megapascal. So entropy, how much entropy? 6.75. So 6.75 will be somewhere between this value, right? So you can use the interpolation and you can find the required values. Okay, so H will be between these values. Okay, so you can use some linear interpolation or higher order interpolation. I am taking the value 3204.9. Okay, H4 is equal to 3204.9 kilojoule per kg. Okay, so please try to calculate this value by yourself. Okay, now coming to 0.5. So 4 to 5 is constant pressure heat addition. Okay, so P5 will be equal to P4, right? And that is equal to 4 megapascal. And temperature is given to be 550 degrees Celsius in the question. So again, you will have to use the same table with this pressure somewhere between this value. Okay, So again, you'll have to use interpolation. I'm writing the direct values. Okay, so please try to do this by yourself. H5, I am taking 3559.7 kilojoule per kg. Okay, so it should be somewhere between this value. Okay, and S5, this should be somewhere between this value. Okay, so I am taking 7.2335 kilojoule per kg Kelvin. Okay, now coming to point 6. So 5 to 6 is an isentropic expansion. Okay, so entropy at point 6 will be equal to entropy at point 5. Okay, and pressure at point 6 is given to be 2 megapascal. Correct. Secondary heat is at 2 megapascal. So we will use 2 megapascal values. Where is 2 megapascal? 2 megapascal. And the entropy is 7.2335. So 7 to so it should be somewhere between here, right? Somewhere there, correct? So again, I'm taking the direct values. So enthalpy should be somewhere around uh, this value. Sorry, this is internal energy. Enthalpy should be somewhere around this value, between 3200 to 3400. Okay, I am taking 3321.1. You can do your own interpolation. Okay, so similarly, we can find the values at 0.7. So 6 to 7 is constant pressure heat addition. It is again 2 megapascal pressure at 0.7, and temperature at 0.7 is again 550 degrees Celsius. It is given in the question. So 550 is here. Something somewhere around this value. Okay, again I am taking the direct values. So at 7 I am taking 3578.4 kilojoule per kg. As 7 is equal to 7.5706 kilojoule per kg Kelvin. Similarly, at point 8 you can find the values using the table. Okay, so in this question there is nothing special, only you need to look up the tables again and again, and you need to churn out the values using some interpolation, or nowadays there are some softwares, if you give the values uh, some properties and it will give the remaining properties. Okay, so at point 8 again I'm writing the direct values. You can check the table and do the required interpolation. So I have these values. P8 is equal to 30 kilopascal. It was given in the question. S8, from S7 to S8, this was isentropic process, isentropic expansion in the turbine. So from these values, you can use the saturated table and you will get the quality of steam to be like this. Okay. If you find these values, you need SF from the table and latent heat from the table. S8 you already have, right? That is equal to S7. If you substitute the values, you will get uh, the steam quality. Okay, so let us substitute the values. Sorry. Zero 0.6 minus 0.0. So quality you will get at 0.8 is equal to 0.9711. Okay, so you can calculate the enthalpy at 0.8. This will be equal to enthalpy of saturated liquid into steam quality into the latent heat. Okay, again just substituting the values. 89.27 plus 0.97. So enthalpy at 0.8 you will get 2557.1 kilojoule per kg. Okay. Okay. Now we have all the values. So this was quite, time-taking process, checking the tables again and again, doing the interpolation. But in the exam, either you will be giving the direct values or you will be provided with the steam tables. Okay. Now we need total heat input. So where is we are providing the total heat in the boiler, then first reheat and the second reheat. Okay. So Un will be the in the boiler. So H3 minus H2. Then first stage of reheat, H5 minus H4. Then the second stage of reheat, H7 minus H6. All these values we have. We just need to put the values. So 3, I'm just writing the values, nothing special. 299.37 plus 3559.7 minus 32. So if there is any mistake in these values, just let me know. 3578.4 minus 3321.1 kilojoule per kg. Okay, so Qin you have 3813.7 kilojoule per kg. And Q out in the heat rejection, that is from 8 to 1, right? Constant pressure heat rejection. So it will be H8 minus H1. Again, you will substitute the values and you will get this final value. Sorry. Two two six 7.9 kilojoule per kg. Okay, so now you can calculate the net work output. So that will be equal to total heat input minus total heat output. So heat input is 3813.7 minus heat output is 2267.9 kilojoule per kg. So it is coming out to be, I'm not doing the calculation, please check it. So 1545.8 kilojoule per kg. Okay, so now we can calculate the thermal efficiency. This is nothing but net work output divided by total heat input. So just substitute the values: 1545.8 kilojoule per kg, and total heat input was 3813.7 kilojoule per kg. And if you calculate this value, then you will get thermal efficiency comes out to be 0.4053. So it is 40.53%. Okay. And in the last part, we have to find the mass flow rate of the steam. So that will be equal to rate of power output, total rate of total output, total power output divided by specific work output. So specific work output is work output per kilogram of steam. So this is given in the question that it has to produce 75 megawatt. Okay, 75 kilowatt divided by network output, which was 1545.8 kilojoule per kg. So we have mass flow rate of steam comes out to be 48.5 kilojoule per second. Okay, so this is the mass flow rate of the steam. This is the thermal efficiency. Okay, so this is what we were supposed to calculate. I hope everything was clear in this question. So nothing special, only we need to check the value from steam table, and uh, everything is simple. We just need to substitute the values and calculate the required quantities. So now we will move to the next question. Question number 6. This is from the refrigeration. So question number 6 says a refrigerant uh, R134A enters the condenser of a residential heat pump at 800 kilopascal and 50 degrees Celsius at a rate of 0.022 kilogram per second and sleeps at 750 kilopascal, subcooled by 3 degrees Celsius. The refrigerant enters the compressor at 200 kilopascal, superheated by 4 degrees Celsius. We have to find the isentropic efficiency of the compressor, the rate of heat supplied to the heated room, and the coefficient of performance of the heat pump. We also need to find the coefficient of performance and the rate of heat supplied to the heated room if this pump operated on ideal vapor compression cycle between the pressure limits of 200 and 800 kilopascal. Okay, again, this lengthy question. So let us try to solve it quickly. I will not open the steam tables. Wherever the properties of steam is required, I will write the direct values. Okay. So you can use the not the steam table. Okay, you need the property table for R134A. Okay. So let us make the TS diagram first. So 1 to 2, it is the compressor. Then condenser, 2, 3. Then 3 to 4 is the throttling valve, and 4 to 1 is, you know, the evaporator. Okay. So I will write the values. P2 is equal to 800 kilopascal, T2 is equal to 50 degrees Celsius. It is given in the question, and from the property table of this refrigerant R134, you can find the enthalpy value at 0.2. It is coming out to be given in the table like this. Okay, so at T3, so 0.3 is at the saturation line. So at 0.3, not at the saturation line, it is near to saturation line, and it is subcooled by 3 degrees Celsius. Okay, so T3 is first you need to find the saturation temperature at 0.3. So at 0.3, pressure was how much? 750 kilopascal. So at 750 kilopascal, the temperature is 26.06 degrees Celsius, 29.06 degrees Celsius. So it is the saturation at 750 kilopascal. Okay, so but it is subcooled by 3 degrees Celsius. So it will be -3, right? So 29.06 degrees Celsius minus 3, correct? So it is 26.06 degrees Celsius. Okay, so at this value of temperature and 750 kilopascal, you can find the enthalpy from the property table, and it will come out to be 87.93 kilojoule per kg. Okay, and H4, H3 to H4 can be considered to be an enthalpic process. So H4 will be nearly equal to H3. Okay, that is equal to 87.93 kilojoule per kg. This is H3, right? Now at 200 kilopascal, okay, at 200 kilopascal, we can find the saturation temperature, and it is minus 10.09 degrees Celsius, but it is subcooled by 4 degree. So T1 will be equal to minus 10.09 degree. Sorry, superheated by 4 degrees Celsius. So plus 4 degrees Celsius. So it will be the T1. Okay, and P1 is 200 kilopascal. So at these values, you can again find the enthalpy and entropy. So 47.88 kilojoule per kg, and entropy will come out to be 0.9507 kilojoule per kg. Okay, you please check the tables. So P2 is 800 kilopascal, and S1 to S2 is isentropic, so entropy will be same, right? 0.9507 kilojoule per kg Kelvin. Okay, so at this value, you can find isentropic process. By isentropic process, you can find the enthalpy at 0.2 S. So 0.2 S. So 0.2 S is the endpoint of an isentropic compressor. Okay, so now you have all these values. Now you can calculate whatever is asked. Okay, so what we are asked? We are asked to find the isentropic efficiency of the compressor, so that you can find as isentropic compressor work divided by actual compressor work, right? You just need to put the values. So this is the isentropic efficiency. In the second part, we are asked to find the rate of heat supplied to the heated room, right? So rate heat supplied means how much heat is being rejected, right? So that is nothing but QH, heat rejected at higher pressure, higher temperature. So that will be equal to mass flow rate times H2 minus H3, right? Again, if you just substitute the values, mass flow rate is given in the question, 0.022 kilogram per second, and H3 and H2 we have already got. So this value is coming out to be 4.373 kilowatt. Okay. We have to find the COP of the heat pump. So COP of heat pump will be how much heat is being uh, given to the heated room. COP will be how much heat is given to the heated room divided by work input. Okay, so 4.373 divided by work input. Work input is 0.8542. It is coming out to be 5.12. In the last part, it is asking to calculate COP and rate of heat supplied to the heated room if the pressure range were 200 and 800 kilopascal. So it is exactly the same thing, only the pressure values are changed. So we again need to check the property table for this R134A, and you need to repeat the whole process. Okay, so we are not going to do that because we are running out of time. but concept is actually same. The only thing is you should know how to check the steam tables in the exam. Either you will be given the direct values, or you will provide, or you should be provided with the steam tables. Okay, so we have calculated the isentropic efficiency, the heat supplied to the room, and the COP. Okay, so part D will have the similar procedure. Okay. So there is one question which we had in the session for refrigeration and air conditioning, but we left that question because we had not studied the air compressor. So now, because now we have studied that, so we can solve this, right? Okay, so the question says prevent 12. Okay, so uh, this refrigerator producing a cooling effect of 20 kilojoule per second operates on a simple cycle with pressure limits of 1.509 bar and 9.607 bar. The pressure leaves the evaporator dry saturated and there is no undercooling. We have to find the power required by the machine. Okay, and there's some information given about the compressor. Okay, so if the compressor operates at 300 rpm and has a clearance volume of 3% of the stroke volume, we have to find the piston displacement of the compressor. For the compressor, assume that the expansion follows the law of P V to the power 1.13 is equal to constant. And we are given some properties of this refrigerant. Okay. So from the table, what we have? From the table, we have H2 equal to, first we should make the diagram, then it will be, easy to understand. The TS diagram. Okay. So 1, 2, 3, 4. So in the table, what is given? H2 is given 178.61 kilojoule per kg. H3 for the isentropic case, it is given to be 203.05 kilogram per second per kg. Sorry. Enthalpy of saturated liquid at 0.4 is given at 74.53 kilojoule per kg. Okay, and this is H1 because 124 is isenthalpic process. Okay. And we know that cooling effect is given by evaporator. Okay, so that is equal to m into H2 minus H1. Okay, so this is evaporator. If we substitute the values, cooling effect, it was given in the question that it need to produce 20 kilojoule per second, right? So 20 kilojoule per, I'm not writing the units. So m dot is the mass flow rate of the refrigerant, and H2 and H1 we have, just substitute the values. So 178.61 minus 74.53, and you have the m2. Just calculate this value. I'm not doing the calculation, I'm writing the direct value, and I have this value 0.192 kilogram per second. Okay. We also know that 2 to 3, this is isentropic compression. Okay. So S3 will be equal to S2. Okay. And from your thermodynamics, basic thermodynamics, you know this relation. Okay. This we have. Okay. Now if you substitute the values, so what we get, 0.682 plus Cp is 0.747 ln T3 313 is equal to 0.782. Okay. So from this equation, you can calculate the T3. I'm not doing the calculation. Just I request you to please do it. Try to do it by yourself and check if you are getting T3 is equal to, I am having this value, T3 is equal to 324.2 Kelvin. Okay, please do this calculation. It's simple like log. Okay. Now we have temperature at point 3. So you can calculate H3. H3 will be equal to H3 dash plus Cp minus 303. Okay, so if you calculate and substitute the values, you will get 203.05 plus Cp is 0.747, 324.2 minus 303. So we'll get the enthalpy at point 3, and it is coming out to be 211.4 kilojoule per kg. Okay. So how much power is required to run the compressor? Compressor is 2 to 3. So how much power is required? Power required will be equal to m dot H3 minus H2, right? And if you substitute to the values, M3 we have got, H3 and H2 also we have, and if you just substitute the values and calculate, you will find out that power required is 6.29 kilowatt. Okay. And since you have studied about air compressors, so now you can easily tell that piston displacement, how to calculate the piston displacement. You know the volumetric efficiency in terms of clearance volume. It is 1 plus C plus minus C to the power PD by PS power 1 by N. Okay. So C is the clearance volume. And if you substitute the values, clearance volume was given to be 3%. So C will be 0.03 minus 0.03 into 9.607 divided by 1.509 to the power 1 by 3. And if you calculate this thing, this comes out to be 0.876. That is equal to 87.6%. Okay, so this is the volumetric efficiency. we have to calculate the power required by the machine and piston displacement. Okay. If we want to calculate the volume of refrigerant at the intake conditions, we can write it as m dot into a specific volume. So this will be equal to 0.192, that is the mass flow rate of refrigerant, and the specific volume is 0.1088. So we will get 0.02089 meter cube per second. So swapped volume will be equal to the volume of refrigerant at the intake divided by the volumetric efficiency, right? So volume of the refrigerant at the intake is 0.02089 meter cube per second divided by the volumetric efficiency is how much? 87.6%. Okay. So it will come out to be 0.02385 meter cube per second. So swapped volume is, what's the RPM? 300 is the RPM, rotations per minute, and this value is in per second. So we need, but we need the swapped volume. So we need to divide by the number of revolutions in 1 second, right? So 0.02385 divided by 300 by 60. Okay. So swept volume comes out to be 0.00477 meter cube. Okay. So this is the swept volume. This is the volumetric efficiency. And power required is power required is 6.29 kilowatt. Okay. So this was the combination question based on the combination of concepts from refrigeration and from the air compressors. Okay. So I hope this was clear. We have one more question, but I don't think that we can solve this in the remaining time. But I will explain how can we solve this. So let us quickly read this. So question 8 says, a piston cylinder device contains 0.05 meter cube of gas initially at 200 kilopascal. Okay. So at this state, a linear spring, that is a spring constant of 150 kilonewton per meter, is touching the piston but exerting no force on it. Okay, so there is one spring that is touching the piston, but it is not pushing or pulling the piston. It's just free spring. Okay, and it is a linear spring, so the force will be proportional to the displacement or the compression or the elongation. Okay, so the force is proportional to the displacement. Okay, and now the heat is transferred to the gas, causing the piston to rise, right? Because if you are adding the heat, so there will be a pressure rise, so the piston will move up. So now heat is added to the gas, causing the piston to rise and compress the spring until the volume inside the cylinder doubles. Okay, so when the piston will move up, because the pressure is being built up because you are adding more and more heat, so it will move up. Okay, but there will be compression in the spring, so it will push the piston down. Okay, so at some point there will be equilibrium. Okay, the force of piston and the force due to the pressure inside the cylinder, that will be equal to each other. Anyways, so if the cross sectional area of piston is given, it is 0.25 meter square, we have to find the final pressure inside the cylinder and the total work done by the gas and the fraction of this work done against the spring to compress it. Okay, so this is quite easy question. Okay, so we have the initial volume, right? And it is saying that after the expansion in the final state, the volume will be doubled. Okay, so you can find the final volume. Okay, so the final volume will be just the double of the initial volume, right? You have the cross sectional area, you can find the pressure, sorry, you can find the force because you will know the pressure, correct? And since it is a linear spring, so you can use this relation. Okay, and force will be pressure into cross sectional area. Okay, so using these equations and whatever values you have, you can easily find whatever is asked: the final pressure inside the cylinder, total work done by the gas, and fraction of this work done against the spring to compress. Okay, I will not solve this because you can solve it by yourself. Okay, it is just equilibrium, or you just need to equate the both forces: force by piston, sorry, force by spring, and the force due to pressure inside the cylinder. Okay, but I will write the final values. Okay, uh, answer I will write final pressure inside the cylinder. This will come out to be 320 kilopascal. Okay, please try to do it by yourself, and I hope that you will get the same value. If the values are different, there is any mistake, just let me know. Part B, the total work done by the gas. This you will get 13 kilojoule, and work done against spring. This you will get 3 kilojoule. Okay, please try to solve it, and if there is any mistake, just let me know. Okay, so thank you. This was our final session. I hope that these sessions were helpful for you in clarifying your doubts and helpful for you in solving your assignment problems. I hope you enjoyed these sessions. Okay, so today we solved some numerical problems. I tried to cover one problem from each module, but within the time limit, whatever we could solve. But please note down this question, or you can take the screenshot, or you can just note it down and try to solve, and try to solve it by yourself and check if you are getting these answers. Okay, so we will stop here. So I thank you. Okay, so we will stop here. Okay, thank you. Take care.